Testing, 1, 2, 3, testing. Hello, this is Patrick Hill from Triple Point Environmental. I'm going to be starting this webinar now. I thank you all for attending. I hope you get something out of it. We're going to talk about cost-effectively meeting new lagoon ammonia effluent limits for lagoon systems. So this presentation is really broken up into two different parts. I'm going to talk briefly about Triple Point, what we do for those of you who may not be as familiar with us. But then I'm also going to talk about an overview of the lagoon ammonia problem, some of the causes and effects of ammonia pollution, basics of ammonia removal, and then start talking about some of the different alternatives, the ways that we see out there that people meet ammonia limits, and trying to get a sense of comparing costs between those two things. So firstly, Triple Point, we have a motto, we have a belief, and it's lagoons do it better. And we know this is not the conventional engineering wisdom, and that there are a lot of sort of currents within the engineering world that says, oh, lagoons are old technology, they can't treat nutrients, they can't get the job done. And we believe that, so we find it as our mission is to help lagoons do it better. And we know from our experience that a properly designed lagoon system with the right equipment in place can meet any nutrient limit that's out there. We know this because this is what we do. So we've got systems that are in place that are meeting single-digit BOD, TSS, zero ammonia or non-detect ammonia, and we've seen systems even reach very low, down to 0.1 phosphorus. As well, and under 5 total nitrogen. So it's possible to do this with the right equipment in place. And the reason we like lagoons so much, and the reason we're trying to, we're on this mission to help lagoons do it better, is that they're the most cost-effective and easy to operate systems that there are in the world. It's the easiest wastewater treatment system to operate in the world. And so for the communities that they serve, for the industries that lagoons serve, it really is the best solution from a cost point of view, assuming you have the space and assuming you can upgrade the existing facility, which in pretty much all cases you can. The third thing about lagoons do it better, as we found, is that we're getting more and more data and independent research that is coming back and confirming this belief. 2 studies I'll cite. One was done by CH2M Hill, or it's now formerly CH2M Hill, now it's Jacobs Engineering, that looked at the Eagle Sanitary District in Eagle, Idaho, and looked at all the different upgrade options for that. They had an existing lagoon system, they looked at SBRs, they looked at ox ditches, all the different options. And what they found, this PhD over there at Jacobs, was that for the Eagle Sanitary District, no question, the lagoon was going to be the most cost-effective and best option for them over the life of it. The second study that we like to cite was done by the University of Illinois that looked at lagoons and looked at their ability to treat some of the more microcontaminants, things like human hormones or pharmaceuticals that find their way into our wastewater. And what they found is that lagoons do a very, very good job of treating most of these contaminants, and can get up to 95% removal in some cases of these contaminants. And so we found that through that research and other research that I find, and we collect all this data, that really lagoons, this perception is changing. So our mission as a company is to help lagoons to do it better, and we have developed a certain number of technologies to accomplish this task. So our Mars aeration system, which I'm not going to talk too much about today, is a mixer and an aerator in one portable unit, a very efficient way to upgrade a lagoon to help improve aeration, improve BOD removal and mixing. Our nitrox system is a, almost like a post-lagoon nitrification reactor that I will be talking more about today. And this is the idea behind this is, let the lagoon do what it's always done, treat the BOD and TSS, and then we'll take out the ammonia through the nitrox system. An adder on to that is our nitrox plus D system, which is a denitrification system that helps to obviously get rid of that nitrate and convert it into nitrogen gas so we can bring down the total nitrogen. And then finally, we have our Phosbox Lagoon phosphorus filtration system, which is designed to be right at the back of the plant. It can be used for tertiary filtration, or it can be used for phosphorus removal, or both. It can really get that BOD and TSS and phosphorus down to a really low level. So we feel like we have a solution across the board to help lagoons to meet the challenges of these new nutrient limits. We, in this mission, it's not just about selling our equipment in terms of lagoons do it better. We really, really do just want to help the community, and that's why we do these webinars. We want to change the perception that lagoons are old technology, or that they can't treat the nutrient limits, or that lagoons smell, or whatever the lagoon problem that you want to throw out there as a poster child, or one would want to throw out there as a poster child to say why lagoons are not good. We really try to educate people and help them to overcome those challenges, whether we can sell equipment towards it or not. So we have blogs, we have educational videos on our website. I'm a YouTube star personally, and our Lagoons Do It Better TV channel on YouTube. We have training events that we do, and we have a Facebook community to try and connect operators with operators so that lagoon operators can kind of help them do it better. So if you go online to our website, go to tpenv.com/LDIB and register there. We'll send you a Lagoons Do It Better camo hat, a sticker, kind of like a care package, so you get a little bit of free swag. If you're interested in that, please, we're more than happy to do that for you. So now onto the presentation. What is ammonia? So ammonia is a compound of nitrogen and hydrogen. It's a colorless gas with a putrid smell. So I always use the analogy of cat urine. Cat urine is ammonia. It smells like ammonia, and that's just what ammonia smells like in its very pure form. And so when it gets into our water, most of it gets converted into NH4 or ammonium, which is the ionized ammonia. But some of it remains as a gas in the gaseous form of ammonia, which is NH3. And that's what tends to be the harmful aspect of ammonia, and that's what tends to be regulated on your permit. So when you're looking at different forms of nitrogen, ammonia nitrogen is a combination of NH3 and NH4. So that's ammonia, NH3, and ammonium, NH4. Other forms of nitrogen are nitrite and nitrate, and then organic nitrogen. So all these together make up total nitrogen. So when they're referring to TN or total nitrogen, that's what you got to get rid of all these things basically in order to hit a total nitrogen limit. Now, the other form, category you typically see is TKN, which is total kenjajoule nitrogen, and that's the combination between ammonia nitrogen and organic nitrogen. And then the other category you typically see is TIN, or total inorganic nitrogen, which, as the name suggests, is total nitrogen minus the organic component of nitrogen. So typically, in a municipal setting, ammonia mainly is going to come from our urine, basically, and that's the big component of where the ammonia comes from. But if you have industrial sources, there can be lots of industrial contribution. Food processing has a lot of ammonia in it. Any anaerobic digestion process will produce a lot of ammonia typically as a result of it. So, landfills have a lot of ammonia, for example, in their leachate, because a landfill is in effect an anaerobic digester. is really what it is. Very, very, very slow anaerobic digester. And so the leachate tends to have a lot of ammonia in it. Ammonia is used in cleaning products. Window cleaner typically has a lot of ammonia in it. And so all these different sources can combine. And so we often run into a lot of industrial applications where there's, 1,000 or 2,000 milligrams per liter of ammonia. And we run into a lot of municipal applications where there's 30 milligrams per liter of ammonia. So the reason ammonia is such a concern and why it's regulated is that it's very toxic to amphibious life. So it is really like a bullet to the head to a lot of amphibious species like fish, snails, different, and the sort of the basis of a lot of the ecosystems that it finds itself in. So what they found with these studies is that it can it can deplete populations, and it can affect the size of fish. And on a greater scale, ammonia ultimately it finds its way into our waterways just like all the nutrients do. And if you're kind of in this Midwest catch basin, for example, the Mississippi watershed basically encompasses most of the Midwest. So all that water just feeds right down into the Gulf of Mexico, right? And lagoons specifically, make up about 1/3 of all wastewater treatment facilities in the country. So when you think about that, that's, approximately 60,000 lagoons, 6,000 lagoons nationwide. And so, it can be a big contributor into just that one watershed, but certainly other watersheds as well. And that's why it's such a focus for concern, because mainly because of how much ammonia can find its way into the water and ultimately into the Gulf of Mexico. So if you look at it and say, we had, run the numbers on it, we have 3,000 lagoons within the Mississippi watershed. And, the average flow of those lagoons is 300,000 gallons a day. The average ammonia concentration is, 40 milligrams per liter, which is maybe a little bit high. If you do those numbers, that's a discharge of, 300,000 pounds of ammonia per day into our watershed. So obviously that's going to cause a lot of destruction. And so that's one of the reasons that lagoons are being singled out, just like any plant's being singled out as a contributor to ammonia. Ultimately, it finds its way down into the Gulf of Mexico, and as you may or may not know, there's an area in which it's called the Deadzone, right off the coast, where really very little aquatic life can live. And part of that is the ammonia input, part of that nitrates and other fertilizers that are running off farm fields and things like that. But it's a huge environmental disaster. This is kind of what it is. And so anything we can do to treat the ammonia upstream is really going to help the ultimate greater environment. And that's why a lot of regulators in the EPA are really trying to clamp down on ammonia discharge. So how do we typically deal with nitrification? And I mean with ammonia. And I'm not going to talk about, there's several different ways that people approach getting rid of ammonia. Nitrification is really the focus of this presentation, but you can do ammonia stripping and other ways to get rid of it. And so the reason that I'm focusing on nitrification, because this tends to be the most cost-effective approach. And I've seen this even pen out cost effectively up to 500 or 1,000 milligrams per liter of ammonia versus, say, ammonia stripping, which can be very expensive even at very low concentration. So nitrification is the process of using biology, using a special type of bacteria, fostering the growth of a special type of bacteria, which then convert the ammonia first into nitrite and then into nitrate. And so that's the goal, right, is to create the conditions for this nitrification to occur. And in order to do that, you've really got to understand the type of bug, to use kind of a shorthand, that wants, that you need to foster. And then you've got to create the conditions for that bug to grow and to thrive and to do its job. And so in any wastewater plant, you've really got two different types of bacteria. You've got your heterotrophic BOD consuming bacteria on the one hand, and you've got your autotrophic nitrifiers on the other hand, right? And the BOD heterotrophic consuming bacteria, these guys, they do most of the work, right? They're consuming, if you consider that a typical municipal system might have 150 to 200 milligrams per liter of BOD coming in, they're consuming that. They're also way less sensitive to temperature and different conditions within the lagoon itself. They're just kind of the steady eddy, reliable. They're very adaptable to any different type of condition, and generally tend to get the job done and have been getting the job done within a lagoon system for literally thousands of years. On the other side of that, the nitrifiers, in contrast, are much more difficult to foster. They take longer to mature, they're less competitive for the food, and they have very specific needs in order to get them to grow. And so that's the real big challenge in nitrification, is how do you get these nitrifiers to grow, right? And so we've identified 6 different conditions, 6 different key things you got to do within a lagoon to get these nitrifiers to grow. So the first one is to reduce BOD. The heterotrophic BOD consuming bacteria are kind of like the bullies in the schoolyard, right? They're going to eat first. They're going to go and get that pizza that's sitting there on the table and push the autotrophic nitrifiers out of the way on the way there, and stomp on their heads while they're at it. And so you've got to get the levels of BOD down to 20 or 30 milligrams per liter. Typical is kind of the range before you really get fast nitrification, and you really can create, you can what we call select for the nitrifiers in the reactor. The second thing about the nitrifiers is that they need a lot of oxygen. And so if you look at BOD consuming bacteria, right, the heterotrophs, we design a lot of aeration systems. We do a lot of retrofits with our Mars system, for example. And typically our basis of design is we're going to find out how many pounds of BOD are coming into the system, and then we're going to add 1.5 to 2 pounds of oxygen per pound of BOD coming in. So this is very standard basis design for any type of aeration system. And then on top of that, we're going to add we're going to say we want buffer. We want a little extra oxygen in the water. We want dissolved oxygen, and that's typically anywhere between 0.5 and 3 milligrams per liter of dissolved oxygen. And this is just extra oxygen you need in order to make sure that you're never going to run out, basically, and you don't get a septic condition. Now, when it comes to designing for nitrification, you need to have 4.6 pounds of oxygen per pound of ammonia, so significantly more oxygen per pound than you need for BOD removal. And then you need to run those DOs, especially at colder temperatures, is what we found, at 4 to 8 milligrams per liter. Sometimes in the summer, you can lower that down to 3 milligrams per liter, and the nitrifiers will be just happy as clams. But in the winter, we found in order to really promote the cold weather nitrifications for reasons that I'll explain in a minute, you want to really run at that higher DO. And then finally, mixing is really, really critical. The thing about lagoons they're so big, right, that it's almost impossible to completely mix them. And if you do want to completely mix them, it requires a lot of energy. Now, if you're trying to just treat BOD, you don't need as much mixing as if you're trying to do nitrification. Nitrification requires a lot of mixing, and part of the reason for that is that you're trying to get the bug, the food, and the oxygen together. And the better job you do that, right, you get the nitrifier, the ammonia, and the oxygen all in one place, the more nitrification you're going to be able to achieve, and the faster time you're going to be able to achieve it, and the more reliable you're going to be able to achieve it. So you got to have that mixing in place in order to make sure that you're going to get the full nitrification potential out of your system. The third thing, is really important is alkalinity. So alkalinity is what the nitrifiers consume when they're converting that ammonia first into nitrite, then into nitrate. So typically, like, we run into issues with alkalinity a lot in industrial applications where there's no background alkalinity within the water, or there is background alkalinity within the water. However, there's not enough to nitrify enough, right? Because for every pound of ammonia consumed, I think you need, and don't quote me on this, I think you need about 1.5 pounds of alkalinity in order to make that conversion. And so if you don't have that right, your pH tends to drop. And if your pH drops, it can really kill the nitrifiers, in essence. Now, municipally, this is generally not a concern. There's plenty of alkalinity within the water to get the nitrification done without having to add any. Industrially, this is of a high concern because a lot of cases, the feed water coming in just doesn't have that background alkalinity. And so it's a big, big thing to make sure you maintain that pH that's optimum for the nitrifiers and you have sufficient alkalinity for them to do their job. The fourth thing, and this is super, super critical, and this kind of dovetails into the fifth thing, is, you know, in order to nitrify, you have to grow nitrifiers, right? You have to have what's called a biomass, a sufficient nitrification mass in order to do the job. Now, nitrifiers are what's called known as an attached growth organism. So they like to grow on things, you know, and so in a lagoon, they're looking to grow on any surface that they can find. They'll grow on the sidewalls of the lagoon. They'll grow on the aerators in the lagoon. They'll grow on the baffle curtains that are in the lagoon, anything they can attach to. And what you often find is that the more surface area you can provide just to the nitrifiers, right, the more nitrification you can achieve in a smaller time frame, right, which makes sense, right? So you got to give the nitrifiers a home to live in, right? And the more homes you give them, the more surface area you give them, the more nitrifiers you grow, the better nitrification you're going to see, and the faster you're going to see it at low temperatures. So we find a lot of lagoons, for example, can nitrify in the summertime, and that they get really great ammonia results in the summertime. They'll get down under 1 in some cases in the summertime. Like, it just comes out and there you go. It's, you know, the ammonia is like, you know, under 1. It's awesome, right? But you get into winter and all of a sudden it just pops up. And the reason is because it dovetails into the fifth point, which is that nitrifiers don't like cold temperatures. Now, no living organism likes cold temperatures. You, me, heterotrophic BOD consuming bacteria, and the nitrifiers. Nobody likes it. Everybody slows down when it gets cold outside, right? But that's especially true of nitrifiers, where, you know, they have a significant drop off in their kinetic rate, what we call the kinetic rate of their ability to digest ammonia with every temperature, 1 degree temperature drop that you see. So you can see this graph here. This is of a system in Iowa that we're actually doing the upgrade on right now. And they have plenty of data from their influent and effluent ammonia, and it's such a very typical as what you see. Summertime, great, killing it, you know, getting that ammonia down. Maybe not quite meeting their permit limit, but pretty darn close, you know, when the water temperature's high enough, right? Then the water temperature drops in the winter, and then all of a sudden nitrification drops off significantly, and then they lose, you know, probably, you know, they're up there. They're 10, 15, 20 milligrams per liter ammonia, and that's not going to hit their permit, right? And so this is where lagoons tend to struggle, and the reason is that nitrifiers are very sensitive to temperature. So lagoons can treat the BOD. Municipal lagoons typically don't have any pH or alkalinity issues. You don't see a lot of toxins in lagoons, like oversupply of heavy metals that will affect nitrifiers. I didn't talk too much about that, but that would be a whole presentation in and of itself. But nonetheless, that's something you need to pay attention to industrially, but municipally, not too much of an issue. However, where lagoons fail is that they fail to have sufficient nitrifier mass, and they can't do it within the temperature due to the fact that they don't have sufficient nitrifier mass. They generally don't have enough oxygen and enough mixing designed into the system. So that's where lagoons tend to fall down when it comes to nitrification. So we're going to talk about some options now. What do you do if you have a lagoon and you need to meet an ammonia limit? So first thing is we're going to talk about, the sort of conventional wisdom, the mechanical plant replacement. Then we're going to talk about a modified discharge. And then finally, what do you do if you upgrade your lagoon, right? And what does that look like? We'll talk a little bit about our nitrox reactor during that process too. So firstly, the mechanical plant upgrade. So this is being kind of the conventional wisdom probably until about 5-6 years ago, I think, where you got a lagoon, it's not hitting its ammonia limit, it's not designed to currently, and people think, well, the lagoon can't do it, so we're just going to get rid of the lagoon. So they come in, they design this nice shiny mechanical plant, gets into place, no doubt can meet the ammonia limit. Mechanical plants have been treating ammonia for years. Small footprint, especially in terms of a lagoon, I mean, it'll fit into 1/10 the lagoon size for the same treatment flow. And then you can, double, triple capacity if you want to within that footprint size. The problems with this approach, and the state of Idaho is a good example of this, where they were sort of actively pushing lagoons out of existence. They were like, they didn't want to permit lagoon upgrades, and so they went in, they put in some mechanical plants, forced some communities to put in some mechanical plants, and then we get 5 years into this, and they're sitting there and they're looking at the data, what's coming out. They're looking at the lagoons, they're still online, and they're looking at the mechanical plants. And lo and behold, the lagoons are putting out way better effluent than the mechanical plants are. And they're like, well, what's going on here? Why are the lagoons doing a better job? They're supposed to be not as good, Well, of course, it turns out that the lagoon was very expensive to upgrade, right? And you can get some grants for these kinds of things, but the city ends up paying a lot of that bill. And then it's very expensive to operate, and they don't have the operations personnel in town that can really effectively operate the mechanical plant, right? And do a good job of it. And so it just, it turned out to be what seemed to be a good idea, a kind of slam dunk, turned into being a bit of a nightmare because of all these external considerations. And so since, I've heard that the state of Idaho has really backed off that policy of trying to push lagoons out of existence and say, maybe lagoons aren't so bad. So that's the big concern. The second thing that we run into a lot is land application. A lot of states really try to push land app, and there certainly are some environmental benefits to land application done properly, right? The nutrients themselves end up getting taken up by a growing crop that is obviously on the ground, and that water doesn't necessarily find its way, or that nutrient-laden water at least, doesn't theoretically at least find its way into the receiving stream. And then beyond that, the rest of the water is able to trickle down through Mother Nature's filter and ultimately potentially recharge the aquifer as well. So it makes a lot of sense. And I'm not like totally anti-land app by any means, but what I will say is that I had some experience with this. I used to work for a company previously to Triple Point that designed and operated land application systems. And it does require a lot of land to build the storage lagoons necessary, because in most cases you can't irrigate 365 days a year. And then it also requires a lot of irrigation land, which generally you can't irrigate on a food crop with wastewater effluent. So you're looking at a non-food crop. In some areas, there just aren't any non-food crops available. Cotton would be a good one, except in a lot of cases, cotton fields are just not available. And so it can be very expensive to acquire that land and take up a lot of area. A lot of folks just end up growing hay, basically, and then they give the hay away in return for somebody coming out there and just mowing it once a year and baling it. The other thing is that land application is, requires maintenance. It's not as simple as it sounds. You've got to, there's pumps involved, irrigation pumps, and then there's an irrigation system, either a center pivot rig or irrigation heads if you're irrigating on, say, a golf course or something like that, that need to be maintained. And that's not, it can be, honestly, it can be difficulty, because I've seen it being difficulty for the operators, that you get clogged heads, or you've got a center pivot rig that has, the wheels are falling off of, or the track needs maintenance, things like that can cause an issue. And then the final thing, I think is the really big thing, is that if you do store, you've got to get rid of the water. And typically you can't get rid of that water within a 24-hour period after a rain event. So you've got to be on it, right? You've got to shut the rig off when it rains. You got to wait 24 hours before you can turn it back on, and you got to make sure you hit that 24 hours, because you need every day you can to irrigate in order to get rid of the water by the end of the year. So it can be really a tricky thing. I'm not saying that it's definitely not a good idea. I'm just saying that it's something that it's not as easy or simple, as straightforward as an idea as some may think it is from an operation and from a capital cost point of view. I just did a video on this, by the way, a video blog on our that we posted this week on our Lagoons Do It Better YouTube channel. So if you're interested in more information about land applications, the pros and cons, feel free to go take a look at that. So the third category of things is to upgrade the lagoon, and this is where we see a lot of facility plans going, and a lot of owners going to, because you've got this existing infrastructure that is the lagoon, right? You don't have the land for land app, or you don't want to do land app. Now, how do we upgrade this lagoon to get this ammonia treatment? So there's really three different options I'm going to investigate here, and this kind of ties into creating the conditions that you need in order to nitrify within the lagoon system. So all these options, what they look at in one form or another is they're looking for ways to add surface area, right, to give the nitrifiers a home, right? And so everybody does it in a different way. And the second thing that folks look to do, in some cases, not all cases, is to control temperature or to mitigate the effects of temperature in one way or another. Right, those are the two key factors, really, is surface area and temperature, right? Biomass and temperature. So one option is that, and I've seen this over the years, is where you just get a media module, right? And in this case, in this picture, you can see here, it's like an engineered fabric, in essence. And you have sheets of this fabric within a square cage, and you just drop that into the lagoon. Right, and it's kind of a neat idea, right? Because you got the lagoon, you got the volume in the lagoon, right? You've already got that footprint there. How can you use it more effectively? Can you just drop this media in the lagoon? And then you have an aeration grid on the bottom of it, right? That is bubbling air through the media and upwards. And then you've got a hose, an air hose going back to a blower, which is sitting on shore. So it's low footprint requirement, somewhat, theoretically low capital cost, low land requirement, easy to operate, things like that. The issues that we've seen with this is that couple ones. First of all, it doesn't seem to work particularly well below 45 degrees C in all the evidence and the data that I've seen. So when that water gets really cold in the winter, there's a drop off in that nitrification that happens through those reactors. And then part of that is just that lagoons get cold, right? Lagoons are one big massive heat exchanger when you think about it. You got the cold winter wind blowing on top of them. You got this huge amount of surface area that's out there, the surface of the lagoons, and they just lose temperature. And that's just fact of life for a lagoon, And so they tend to struggle. The second thing that we've seen is that you can get things that float in the water column. A lot of lagoons don't have any screening of any kind. They'll float. They could get clogged on the cage, get clogged in the material somewhere, somehow. Even if it's turtles or fish or anything like that, they're relatively unprotected from those kinds of, coarse contaminants, basically. The third thing is short circuiting. So lagoons are massive, right? They're really big, and you put these cages in. What is going to cause the water to go through the media? How do you make it go through the media? And invariably, you're going to get some water that goes around the media, under the media, over top of the media. And if the water doesn't go through the media, then you don't get nitrification fully through the system, right? So there's a limited effectiveness. And the other thing is that we have found in some cases where they put this in and they've actually got nitrification for 1 year, 2 years, worked really well, get into year 3, and all of a sudden nitrification drops off. And they're like, wow, what happened, right? And they pull them up, and there's all these little red worms that are growing and eating the nitrifiers on the media. And I kid you not, this is a big thing in lagoons. You get these red worms, and they will literally eat the bacteria. And how do you treat for that? How do you get rid of those? I don't know. It's not my gig, but it's been seen to be a concern. So another option to upgrade a lagoon is to do kind of similar to what I showed you on the nitrox. You treat the BOD through the preceding lagoons, right, just like you normally would. And then right at the back of the process, right before you discharge, you add what's called an aerated rock filter. And this is a hole in the ground, basically, that you put an aeration grid on the bottom of, and then you fill it full of rocks. Right, and these things can be really big, right? They're designed. The principle of design is to basically, put enough surface area out there in terms of the rock that the bugs can grow on, that you've got so much surface area that you can overcome the really, really slow treatment you get in winter when it's cold outside, by the fact that you've got so many nitrifiers out there that even if they're eating slower, they're still eating and they still consume the ammonia. And so these systems are been tried and true and tested. I mean, they've got these things operating in Manitoba, Canada. I was just there last week. It was summertime, so it was warm outside, but I've been to Manitoba during the winter, and it is the coldest place on earth that I've ever been to. And I haven't been to Antarctica, but it was brutal. Minus 20 degrees at the end of November last time I was there. Fahrenheit. And so that is ridiculous. And so they've been using this technology probably for 10 years or 15 years, I think. Great cold weather nitrification. Cannot touch the numbers. I can't touch them. I can't criticize it all in terms of the treatment performance. And it's a low maintenance system, right? I mean, it's simple, one pass. Got the blowers on, you run the thing, it goes, it does the job for the most part, The issues I've seen with it is the high capital cost. These aerated rock filter cells tend to be big. I mean, they're like, almost like football field size, depending on your flow rate. And so you need the land if you don't have the land, and you got to truck in a lot of rock. And that cost for that rock highly depends on where it's coming from, right? And how far it's got to be trucked. And I've seen numbers be really vastly different from site to site based on that alone. And in addition to the fact that they're really big cells. And the second issue that I've seen with this system is that basically, like I said, in essence, what it is an aerated rock filter. And in lagoon history, I'll give you a little walk down memory lane in lagoon history. There was a time in the 80s and the early 90s where a lot of lagoons had rock filters at the back of them. Different design than this, but similar principle, right? Where they would put these pile of rocks right near the effluent to the plant. And the idea there was to maybe create a little attached growth, but also to mitigate algae, right? The algae couldn't grow within these rock filters. By about 10 or 15 years into this experiment of using these rock filters, every single one of them plugged. And the reason is because lagoons, algae can plug these things. Lagoons also have seasonal turnover events, which, lagoons they build up sludge. And when you have lagoon turnover, that kicks some of that sludge into the water column, and of course that gets carried down the line. And you'll see this in lagoon effluent numbers, that BOD and TSF can be higher in the spring than it is in the summer or in the winter because of this seasonal turnover that occurs that's just natural to lagoons. And so, the problem, of course, is that you have an aerated rock filter, but it's a filter that can't backwash itself, right? And if you don't have a backwash mechanism for any filter, there's always the potential to clog. So that is a big kind of long run concern. The second option in this vein, or third option in this vein, before I get onto the nitrox, is takes a slightly different approach. What it does is it says, hey, why are we losing all this heat in the lagoons? Well, it's because we got this big surface area. Well, what if we covered and insulated that surface area? What if we put a floating insulated cover on the surface? And at first, it kind of sounds crazy. It's like, no, wait a second. These lagoons are huge. You can't put a cover on these things. But when you do this, and this company sold a lot of these systems, and you aerate underneath the lagoon, you keep the temperature in, you can get that nitrification, right? And so that's exactly what happens. So they have a lagoon system. Typically, it's a 3-cell lagoon system, 2 aerated cells, 1 polishing cell. It's all covered. And then they'll also have a tertiary attached growth reactor right at the end of the process, just for polishing, what they call a polishing reactor. That can grow some nitrifiers and do whatever nitrification can be done, but they don't ever allow the temperature to fall far enough where they lose that nitrification, even in the winter months. And so, again, been around for a long time, really good treatment, can't touch the numbers, great numbers. The issues that I've seen with it is, again, capital cost. When you're covering a huge lagoon, that's going to cost a lot of money, and that's just square footage. It's a simple numbers game to figure out. You're going to pay $3 to $4 a square foot for just the cover alone, and then you got to buy the equipment and all the above. The second thing is that I've seen, like the highlight, is just the maintenance. Number one, you can't see the aerators on the bottom, right? So they're sort of outside, out of mind. And so a lot of folks, even though you can walk on these covers, nobody wants to. And so a lot of folks fail to maintain the equipment. And that's a big complaint that I've gotten from engineers that have spec'd these before and operators of these things. Like, I can't see what's going on the bottom. Like, I can't see the aerators and I can't maintain them. The other thing is the covers, they require maintenance too. They're not going to last forever. Anything breaks down with enough UV sunlight beating down on it all day for 365 days a year. And so in the end, you're going to have to maintain the equipment, which is hard to do. And as the cover breaks down, it's hard to access the aerators, and nobody wants to walk on the cover. And eventually you have to replace the cover. When you go to replace that cover, that's a huge expense. It's almost like buying 50% of the system from an equipment point of view that you bought 10 years ago or 15 years ago when you originally bought it. So it's a big concern in terms of cost. So we've seen that be quite high, probably, well, I'll go through the numbers here in a minute, but one of really the highest cost option when you pen out all the numbers. So we looked at all these different options when we were looking to come up with a nitrox system, and we were thinking to ourselves, man, nitrification is expensive. It just seemed to us like you could treat 1,000 milligrams per liter with a BOD using aeration for a fraction of the cost of putting in a nitrification system, a quarter of the cost of putting in a nitrification system for 30 milligrams per liter. And so we're just like, man, there's got to be a better way to do this. So we looked around and we thought, well, we like the idea of using the existing lagoon infrastructure, trying to leverage it to what's there. And so that's exactly what we do. We've got Lagoon Cell 1, Lagoon Cell 2, then through the nitrox. So we rely on the lagoons to do what they do best, which is to treat the BOD, right? And they can be aerated, they can be facultative. We don't really discriminate between the two. And so it could be either. You just got to get the BOD down to 30 or 40 milligrams per liter. Then we pull it through our 2-stage nitrification reactor, and then into a polishing cell, which is existing, or we create one, or we can use tertiary filtration equipment if necessary, and then out the system. So the first thing you can see here is it's very, very small footprint relative to the lagoon size. So I've yet to find a site, even really tight sites, where we can't fit these reactors on. They will fit in a very small footprint, right? So that's a really, really big cost saver in a lot of these applications. So how do we do this? Well, we do it by fostering the growth of nitrifiers. And like I said, you get, it's all about providing surface area. The way we do it is we add these little media pieces. And this is what's known as a moving bed biofilm reactor system. So this technology has been around since, I think, the 70s when it was originally invented, and it's been used for 30 years to nitrify. And so we're using this principle, this MBBR principle of using these little media pieces in order to create a surface area for the nitrifiers to grow on. And the beauty of these media pieces is you can fit a lot of surface area in a really small footprint, right? So if you looked at, that lagoon I showed you earlier, in that earlier slide about, that you need a biomass, you need to grow, and then that in an existing lagoon, the nitrifiers will grow on the surface area of the floor of the lagoon, the walls of the lagoon, the baffle curtain on the lagoon, or the aerators on the lagoon, whatever they can get themselves onto. And you said, okay, well, that's 160,000, square feet of surface area for them to grow on. And you take that and say, well, how much media is that, of this type of media? And you could fit that 160,000 square feet of media within 1/3 of a semi-truck. So you are fitting a significant amount of surface area in a really small footprint. And that's the beauty of the media, which allows you to put a lot of media in there in order to grow as much biomass as possible, which allows you to get that really, really cold nitrification. The second thing that's key about this is that we have an aeration system in here that's creating a complete, highly, highly mixed condition, right? So this is a medium bubble aeration grid, which sounds fancy, but really what it is a stainless steel pipe with holes in it. So it is really, really tough, very low maintenance type thing. And so what that grid does is that creates all the oxygen transfer you need and the mixing you need to get the nitrification, to get that rapid nitrification that you want. It also ensures that no solids are going to settle within this reactor, right? So you don't want any sludge building up in here, and that won't do that. It just creates a bubbling cauldron within the actual reactor itself that prevents any solids from mixing. The fourth aspect of the system is that we will actually regulate temperature in the wintertime depending on where you're located in the country. So if you're down south, and your lowest possible winter temp that you've ever seen is 5 degrees C, then we don't do any heating at all. But if you're in the mid or north part of the country, then we'll often, if we see evidence, we look at the seasonal temperature variations, and we'll actually regulate the temperature of the water at 5 degrees C. And this is what's sort of different about the nitrox system relative to just a simple conventional MBBR system. One of the differences. And so what we know from literature, the reason for this is because what we know from literature and what we know from studies, hundreds of studies have been done in the field, is that you can't nitrify below 5 degrees C reliably within a moving bed biofilm reactor. So we know if we can keep the temperature at 5 or 4 degrees C, then we can guarantee nitrification. And that's exactly what we do. We typically use 3 different approaches, and it depends which approach we choose. Depends on the site, depends on different design considerations. But one is to actually heat the water up using an electric tank heater. So this is a very simple device. You run a current through it, it heats up a heating element and heats up the water. Couldn't be any simpler. The next option is to use a heat exchanger. And we can use natural gas, or propane with a boiler. So we're pumping in cold water on one side of the heat exchanger, hot water on the other side of the heat exchanger to heat the water up and get that heat transfer. And so this has been done, with anaerobic digesters for, forever, really, in order to optimize performance. The third thing is geothermal. That's the other option we have in order to use heating. So you're probably thinking, well, what's this going to cost me? It sounds like you got a lot of water. It's going to cost a lot of money. heat up water. And to some extent, that's true, but it's not as much as you think. And it's very easy to calculate what the kind of cost is. So I'll give you a couple of examples. We did a couple of plants in Missouri where we typically look to see about a 2.5 degree minimum water temperature in the wintertime. And we'll expect to see that for 3 to 4 weeks a year. And you run the math on that, and there's the Hillcrest and the Villages facility. Hillcrest was 60,000 gallons a day. Villages was 100,000 gallons a day. And the electric heating costs were about $1,600 for Hillcrest and $2,700 for Villages. So really, when you look at that in the grand scheme of that, that's not a huge OpEx cost. And so, in fact, we've consulted with the owners of these two facilities over the last 2 years. They've been using the system, and they basically said, like, we haven't really seen any cost difference in our bill in the wintertime. So really, the heaters weren't even being utilized in a lot of cases. And so that's, I think, one of the nice things about the nitrox system is that whereas with the cover system or the aerated rock filter system, you're paying for cold temperature upfront. Right, you're paying for the coldest winter possible condition on day one. Where with the nitrox system, you're only paying for that coldest winter possible condition when you actually see the coldest winter possible condition, right? And so it can fluctuate year to year, and some years can be colder than other years. And so this, I think, it provides a more cost-effective approach over the long run to that. So, similar to other systems, the operational requirements are really minimal with the nitrox system. That's one of the beauties of it. It's very passive. You've got an aeration blower that you got to maintain. That's pretty much the same for everybody. Everybody's got to put a blower in if you're going to do nitrification, whether you're doing a mechanical plant or you're doing a lagoon upgrade of some other kind. So you got belts, filters, oil changes. But beyond that, the heater is going to run when it needs to run. It's on auto. It's just like it's a temperature controller. It's like a thermostat. Turns on when the temperature dips below, turns off. You don't have to touch it. And then you just got to keep flow going through the reactor at all times. The bugs need food to eat. So if you starve them, don't give them any food to eat, they die. And you're starting from square one. But for most operators, this is just very, very simple. They're checking on it once a day, maybe even once a week in some cases, and just making sure that blower runs. So the beauty of the nitrox system is that it's small footprint, low capital cost. So that's really what it comes down to. It's also a really, really passive operating system of the three main advantages. So now that we've looked at all these options, I wanted to kind of give a case study to give some kind of order of magnitude cost, right, to what each of these costs, so you get a sense of how these things typically stack up. Now, I'm going to caveat this with it depends, right? Obviously, it depends on the application. It depends on your situation, and this is not going to be true of every plant, these numbers. And I've taken these numbers from engineers that I've worked with in the past that have done facility plans that they send into the state, basically putting down the cost to each different approach. And so I'm, again, just take it for what it is. Not designed, it's just a generalization and not to be taken to the bank, literally or figuratively. So we looked at the polishing reactor with the cover system. That was most expensive. The In-Lagoon media was the second most expensive option, then followed by the aerated rock filter, and then the nitrox system was significantly less expensive than most other options. And this is what we typically see. And it kind of makes sense, right? The cover tends to be the most expensive because the cover is very large. It requires just a lot of cover to get out there. And so there's a really high equipment cost. The installation isn't as bad from an installation cost point of view, but that equipment cost really drives things up. The In-Lagoon media, as much as you think it would be lower cost than a lot of these options, it doesn't end up being because, for whatever reason, you got to put so much media in the lagoon in order to actually get enough media in there to get the nitrification that you need, that the equipment cost tends to be relatively high. Those media modules, that adds up, and the shipping costs on those modules can add up significantly as well. Finally, the aerated rock filter, which tends to have a lower equipment cost, but the installation cost is high because you got to truck this rock in, and you've got to get a lot of that rock. Versus the nitrox system, which it usually has the lowest possible installation cost of all the alternatives, or close to that between us and kind of the In-Lagoon media side, and lower overall operating costs as well. So again, take it with a pinch of salt, but that's just some of the numbers that we've run across in the past. So I think the point I like to drive home here is that yes, you might have a little bit higher operating costs with the nitrox system if you are heating the water in the wintertime versus some of the other options. But when you model that out and look at it over a 20-year period, it doesn't catch up because the cost of the equipment and the cost of the installation is so much less than the front end. And that is really using kind of a worst case scenario model where you're planning on, 2 months a year at 2.5 degree temp rise, for the entirety of those 2 months. So when you pen out those numbers, even in the worst case scenario, the nitrox tends to be the most cost effective option. Again, take it with a pinch of salt, but this has just kind of been my experience. So just a couple of pictures here of some of the installations we've done. This one is the Hillcrest facility that you saw earlier. As you can see, again, just very small footprint relative to the full lagoon size. Very simple installation. You can put the blowers outside if you want to. You can put them in a building if you'd like. Pretty straightforward stuff. We've seen very, very good effluent out of this plant since we started it up. This table is not quite up to date, but basically zero ammonia out of the polishing pond for 90% of the year, which is extraordinary. I challenge I take the Pepsi challenge with any mechanical plant on this ammonia treatment, so to speak. And then also really good BOD and TSS, averaging in single digits for BOD and TSS over this test period. Really did a good job of removing that as well through the total system. You look at the water coming out of this plant and I'm amazed by it, even though I shouldn't be amazed, but I am. I mean, it really looks like clean water. It looks like a glacial lake, coming out of this effluent pipe. So with that, I will sum up, and we're getting here close to an hour. And so anybody's got any questions, they can type them in the question box on your right-hand side, I believe. And I will do my best to answer them. Okay. So I already have a bunch of questions in here. I'll try to answer them in turn. How does the effectiveness of the triple point system compare to that of circulators? That's one of the questions. So circulators, I assume you're referring to kind of sort of the solar power circulation systems. They're not designed to be aerators, hence the name circulator. And so they do provide some passive circulation because aeration, because they pull water up from the bottom of the lagoon and they circulate it across the surface, which allows Mother Nature to blow across the surface and create some air, add some oxygen to the water. But they're really not a nitrification solution because they are not designed to add sufficient oxygen to achieve nitrification or sufficient mixing. So I think that they're good for like a supplemental use case scenario and de-stratifying the water kind of scenario, and they'll help enhance a facultative lagoons operation potentially, but they're not going to do the heavy lifting that's necessary to achieve nitrification. And that's just, I mean, as far as I'm concerned, that's a fact. Okay. More questions here. Does land application promote odor complaints from surrounding neighbors? We have heard of issues with lagoon odors. Is obviously a big thing. In fact, in the land application video that we just released, we cite a study in there where that was done in Texas that looked at land application system there and compared it to a system, one with aeration in the lagoons ahead of the land app and without aeration with the lagoons ahead of the land app. And so what they found was that the one with the lagoons ahead of it with aeration in it performed significantly better, which is sort of not surprising. And what I mean by performed significantly better was there was lower maintenance, easier operation, lower BOD, less odor. Which is again not surprising. Whenever you see odor in a lagoon, it's a sign of anaerobic digestion, right? And that's what's creating the H2S and the methane that's causing those odor complaints. And so if you don't do a good enough job aerating it, or if there's not enough oxygen in the water column, then you're going to see that anaerobic digestion cause you an odor issue. So yeah, there can be some complaints with odor with land app, certainly with facultative lagoons. If there's too much sludge, that'll happen as sludge is anaerobically digesting. But a properly mixed lagoon, you don't see that. You don't see the odor complaints through land app. Okay, so nitrox versus MBR for ammonia removal. So an MBR, a membrane bioreactor, again, as I said kind of at the end there, I think you're going to see the nitrox do. I mean, you can't beat non-detect ammonia, right? And that's what the nitrox can give you if properly designed and operated, and in most often cases does give you. So it's going to perform equally as well as an MBR, assuming that an MBR can reach non-detect ammonia, is sort of the answer to that question. Kilowatt consumption or horsepower consumption per pound of NH3 removed. That is going to be a factor of aeration efficiency. So what determines kilowatt consumption or horsepower consumption is going to be primarily depth of the basin. And we will design for anywhere between 8 or 12 feet of depth, maybe even 15 feet of basin depth in some cases. Reason usually that we play around with those depth numbers is to try and fit the nitrox within a certain footprint. So we need to maintain a certain volume of water within the reactor in order to maintain a minimum hydraulic retention time. So, we need 4 hours of retention time within the reactor at average daily flow. So if we get a tight site, we'll make the basin deeper in order to reduce the footprint and still get the 4 hours. If we get less tight site, then we might make it slightly shallower in order to get the in order to optimize the kilowatt consumption of the blower. So that's kind of a deeper conversation about how blowers work, but that gives it to you in a nutshell. I can't really answer that question because it really, really depends on how deep we design the basin and what the oxygen transfer efficiency is at that depth, plus what the pressure is at that depth, which determines airflow, and pressure, which determines kilowatt usage. So I wish I could be more helpful, but if you do have an application that you're working on, we'll be more than happy to size it up for you, and we can do that math really easily. So this slideshow will be available via, if you want to, we're actually recording this webinar, so we will post this online on our YouTube channel afterwards. For those folks who want professional development hours, please email me or Eve, Bjork, B-J-O-R-K, Bjork, at tpenv.com, or just respond to the email that we sent you advertising this, and ask for your pH letter, and we'll send you a pH letter. So that'll be available to you. Foaming. This will be maybe the last question I'll deal with, since we are over time just about. Foaming can be a concern anytime you're growing new bugs within a system. It happens on activated sludge plants quite frequently, and any plant startup. And so the nitrox will see some foaming initially on plant startup. Usually we can mitigate this by either adding nitrifiers that we're growing in the lab to try and avoid new bug growth, just provide the bugs and make sure they're there. Or we can add defoamer in order to defoam it. But once the system's up and running, you can see some foaming at the, we have covers on it, and you'll see some foaming around the edges, some minimal foaming around the edges. Not generally something to be concerned about. It doesn't tend to leave the tanks at all, but we'll see a little bit. And I think that's just because of fluctuations in flow throughout the day, that's very typical of any wastewater plant. And so generally foaming is not an issue except on startup, and if it is an issue, it can be mitigated relatively easily by adding some defoamer or some additional bugs. So with that, I will wrap up. Any further questions, feel free again to respond to the email I sent you. And I'll be happy to answer. And if any of you got an application that you're working on, please reach out, respond to that email. We'll send you a link to our application data form and get some numbers to you, and you can take a look at it and see where it goes from there. So thanks for joining me today. I hope you enjoyed it. I hope you got something out of it. We will be holding future webinars, so keep that in mind in your emails. If you've got any requests for topics, we're very open to presenting on any topic that anybody's got any ideas on. We're happy to provide our knowledge and share our knowledge to help you guys, help Lagoons do it better. Thanks a lot. I'll speak to you soon. Bye.